Okay, sometimes when I'm doing a problem, I get frustrated and I throw the hat in. I wasn't able to do this, but I watched a video on topological sort, and I feel like I understand it better, so I would like to attempt this again. So if you will forgive me, let's get rid of this, and let's see what we can do here. Okay. Leetcode 2392. Build a matrix with conditions. You're given a positive integer k. You're also given a 2D integer array row conditions of size n, where row conditions of I equals above and below of I, and a 2D integer array column conditions of size m, where column conditions of I equals left of I and right of I. Now, it's worth noting that I did spend 35 minutes earlier today trying to code a solution for this before I got frustrated and had a temper tantrum. So I am somewhat familiar with this problem already. The two arrays contain integers 1 to k. You have to build a k by k matrix that contains each of the numbers 1 to k exactly once. The remaining cells should have a value 0. So look here, 1, 2, 3, all the rest zeros. The matrix should satisfy the following conditions. The number above I should appear in a row that is strictly above the row at which the number below appears for all I from 0 to n minus 1. The number left of I should appear in a column that is strictly left of the column at which the number right I appears for all I from 0 to m minus 1. Okay. So return any matrix that satisfies the conditions. If no answer exists, return an empty matrix. Now, the first thing to notice is that every single number can occupy a unique row and column. Just like here, you see, look. Every row has exactly one non-zero number, and every column has exactly one non-zero number. That is going to make it so much easier on us if we don't have two values fighting for a location, so to speak. So first thing we want to do is make sure that there are no loops. Okay, so we are going to have row mappings is a default dict of set. You know what? No, let's do a set. Okay, and then column mappings is the default dict of a set. And we're going to say, I don't know, A comma B in row conditions. And then it'll be rm dot, rm of A dot add B. And then column conditions, C of M of A. And then we want also the inverse. So inverse, and this will be copy, inverse, and B comma A. Now, first thing we want to do is make sure that there are no loops. So, loop found. Now we will have a dictionary, and we will have a point, and we will have a scene. So when we enter, we're going to say s equals s dot copy and s dot add p for position, I guess. Now, if p in s, actually this can go above. If p in s, then return true. Okay. Now we are going to say if p in s, then return true, and then if p not in d, then return false. That means that we are at the end of the chain. Otherwise, for I in d, for I in D of P, then what I don't want to do, the reason I didn't just do this is because I don't want to add an empty set and then not be able to do this anymore. That's why I have two different values here. So if loop found D, comma, I, comma, S, then return true. If in nothing we found a loop, then we're going to just, well, not else, just return false. Okay, and then we're going to say for I in range 1 to k plus 1, loop found dp. The scene would be an empty set. Dictionary is going to be R of M. Okay, if loop found R of MP set, then, yeah, if nothing exists, then we return that. And then we also need to look not just for the rows, but also for the columns. So basically, it's like a topological problem, except it has this little twist where you have to do a double topological sort. But they didn't increase the difficulty any further than that by making it share, you know, rows or columns. So our job is not going to be particularly difficult, assuming we can do the simpler problem. And the truth is, the complexity of solving the simpler problem is effectively identical to the two-dimensional version. You just have to, like, call it twice. Well, just like I'm doing right here. Just, I mean, I'm literally doing the same thing, just with a different mapping. Okay. Now, okay, now I need to build these. So this has eliminated the possibility of a loop. So now we need to find root elements of things that have not been visited. I think that we have reached the point where we need to actually build this, and it's going to be the same algorithm for both R of M and C of M. So we're going to have build order, I guess. Build order, and it's going to have a mapping and mapping inverse. And I guess K, even though K is the same as outside, but whatever. All right, so now this should have a scene equals set, and it should have the output, or, you know, let's not say output, let's say R value, like that. And we will need to do a depth first search, but it should accept, it should start with a root node. So we will do this, and then let's have unplaced equals set of range of 1 to k plus 1, like this. Okay, so we will come in here. Now, if something is placed, I'm trying to think. Okay. Okay, we should have a depth first search of n, like this. This should start with a root node. Yeah. Okay. Now, if n not in mapping, then this means that we are it's the end of the line. What is the word? What's the word for a node that has no children? Oh my God, I should know that. What is the word for a node with no children? Leaf node. Oh my God. Wow. Almost had to turn in my CS card. Okay, so if n not in mapping, then it is a leaf node, which means that we're done. So just return n, like that. And is it non-local? Yeah. Non-local scene. As soon as we've placed something, we're going to say scene.add n. Okay. Okay. If n in scene, wait. If n not in scene, then this. Otherwise, this. Okay, we want to place the children first. All right. Otherwise, there are children that need to be addressed first. So we are going to say for I in mapping of n. And we are simply going to build order of I. Yeah, I guess so. We don't place things until they're a leaf node, and then once all of the children have been accounted for, then if I not in scene, children equals, yeah, children extend that. And then if I not in scene, then scene.add I, and children equals, so this is going to go before, right? And then else well, just nothing. Okay, and then at the very end, we are going to return children. So let's see what this does. Scene is a set. Do I use this? Oh, I haven't even called the depth first search yet. So let's go here. And let's say, let's start with a value. So while unplaced, and then we're going to say v equals unplaced dot, well, let's not pop it. No, pop is fine. Pop is fine. V candidate, let's just say. Right? And then while v candidate is in oh my god, it needs to it can go two different ways. We need a root node. Okay. if v candidate in scene, then just continue. There's nothing that needs to be done. Okay. Yeah, if we trace the parents, then we should find one root. And we only have to go one direction. Okay. So while v candidate in inverse mapping, we don't need to search every direction. We just need to go one direction until we no longer find a parent. So v candidate equals inverse of v candidate. And then this is going to be a list, and we want the first item. Okay. Now, if let's just say v original. If v original does not equal v candidate, which is certainly possible, then we need to put it back. Then we're going to say unplaced.add v original and unplaced.remove v candidate. Okay. Now we do the depth first search. We have a root node, and we should get everything that's attached by doing this. So we are going to say, well, we need to like build an output. That's R values. So R value dot extend, and it's just going to be depth first search. Let's not do this. Let's do new values equals depth first search of the candidate. And I don't think we're going to need this because we are going to do it down here. So for I in new values, we are going to say if I in unplaced, then unplaced dot remove I unplaced dot remove I. Okay, and then simply return value dot append I. And I think that should be it, really. Is this the alignment here? Yes, it is. Okay, so we're going to say rows equals build order of what is it taking? Mapping inverse, and K. And K. And columns is going to be that. And let's look at what this is. Print rows, print columns. That's so that it won't get angry that nothing's returned. I can get distracted by all the red text. First argument must be callable or none. Line 3. Oh. Okay, P not defined. Did you mean PI? Line 27. P. loop found. P is the position. That was a silly mistake. Come on. Required 2 required positional arguments on line 47. Children.extend build order. Not build order. Depth first search. Okay. Unhashable type on line 56. List of mapping inverse of mapping inverse. God, I must be tired or something. Some of these mistakes are weird. Okay. STD out, none, none. That is not reassuring. So, rows, build order. Okay. How could there possibly be less than k entries? That doesn't even make sense. Okay, well, let's try to look at the output here. Print v candidate and new values. One, 3, 3. See, 3 should not appear twice. Well, it's not outputting itself. That is very odd. Well, there's obviously a problem in the depth first search, so let's see here. If n not in scene, then add it to scene. No, this is correct. If I not in scene, children.extend depth first search. Am I misusing children.extend? List.extend Python. Does it update the original list is what I'm asking. Adds the specified list elements to the end of the current list. Yeah. So I is getting added to scene, but not getting added to the final list. That doesn't make any sense. Unless we're like setting scene to true somewhere else. Children equals I plus children. Here. This is going to give us duplicates. Two, 2, 2, 2. There is some reason that it's not attempting to add itself, and we can figure this out here. There has to be some case where n doesn't end up in the list. So it either runs this or this. Now the only way that it can be seen is if it added itself. So this returns n here. If n is in scene, then it means that we saw it somewhere. There's no other solution. Children equals nothing. That's fine. Yeah. For I in mapping of n. Yeah. So whatever it returns, okay. Okay, it's not here. It's not here that it's disappearing. Wait a minute. Well, that should have made it appear more than once. That shouldn't have made it appear 0 times. Well, nevertheless, that was definitely incorrect, so maybe it makes it behave in an unpredictable way. See, the only way that I can get added to scene is if it's added to the return value, right? First search. So 1 and 3. Am I being dumb here or something? Yes. Oh, yes. Such yes. No, that's fine. That's fine. Debugging is part of the process. So 1, 2, 3, 3, 2, 1. Let's get rid of the prints. Okay. Print. These two can remain, but this is what I want gone. Sorry if that was torture and it was obvious what was wrong. Okay. Print rows, columns. Wouldn't it be great if this just worked? Heck yeah. Okay, so the return value. Oh, we have not made a return value. So return value equals boom, boom, 0 for I in range k, for j in range k. Now we need to establish the mappings, right? Yeah, but I mean that should be trivial. So so final row equals yeah, what am I trying to say? 0, not 0. ij for I, comma j in enumerate rows, final column. columns. And then we are just going to say for I in range 1 to k plus, if I could type, to k plus 1, R, so row comes first, right? And then column comes second. Wait, it really is backwards. Equals I. And then we are just going to it's R val, it's not R. All right. One, two, three. 3, 1, 2. Is it backward? Three, 1, 2. Did I get these backwards? That would be kind of funny. Okay, 3, 1, 2. 3, 1, 2. Three, 2, 1, 3, 1, 2. Well, I tried. I really tried. I'm not going to sit here and stare at this for the next 10 minutes trying to figure this out, so I will do one last thing. Okay. Let's say, look at my solution to this Leetcode problem. It is returning the wrong result. Okay. Here is the problem. All right. Can you see my mistake? I'm not particularly hopeful that this is going to find it, but you know, I'm not going to like pester somebody. So if it can see some simple mistake that I made, then fine. But otherwise, just call it good. Determining row positioning. Identifying the issue. Okay, this is taking a while. Okay, the issue with your code lies in the ways you're performing the topological sort of the depth first search function within the build order method. Specifically, you're adding the current node to the result before exploring its dependencies. This results in an ordering where dependent nodes may appear before their prerequisites, violating the conditions specified. Here's the problematic part of your code. Yes, I know. In this implementation, you're adding the current node to children before its dependencies, which is incorrect. For a topological sort and a topological sort, you need to process all of the dependencies of a node before adding the node itself to the result. So something was backwards. It's just saying that I guess this should have gone here instead of here. Yeah, so to fix this, you need to modify your depth first search function to add the current node to the result after processing its dependencies. Here's how you can correct it. Make sure to reverse the R value at the end of your build order function since the nodes are added in post order traversal. Here's the corrected build order function. What the hell? Just copy the whole damn thing. Well, yippee-ki-yay. I guess AI really will replace us. Okay. Well, I don't think that it was all for a waste. I just incorrectly did the depth first search. So if neighbor in mappings, then depth first search neighbor, and then r underscore val dot append. We add scene to here, and then we append at the end. Okay, I guess that makes sense. All right, okay, hopefully I can do it next time. See ya.